just going to talk a bit about the Navier-Stokes equations now. Navier-Stokes equations, basically, using calculus. I've explained what calculus is before. Calculus analyses patterns of movement, basically. Anything that's moving, you can use calculus in theory to study it. I'm not going to talk about who invented calculus and all the intricacies of it, because it's pretty simple when you're actually using it. It's made for a practical purpose. The word calculus might switch you off. It might seem extremely complicated to you. It is, but only when you try and use it to measure things. The actual principle and concept of calculus isn't difficult to understand at all, I don't think. Okay, so I'm going to take the example of a river. Okay, so imagine you've got a river, it's moving along. I want to measure it. Okay, the rate of change, the differential calculus. That's what differential calculus means. It means measuring the difference of change between different points of observation. So the example I'm going to use is, imagine that you sprinkle loads of floating dust of uniform size into a river, okay? And you measure at one point, speck of dust there, speck of dust there, speck of dust there. It's all over the place, little tiny dots. You measure the difference over time between them. This is the differential calculus, like I say. The difference between the change from one point to another point, to another point, to another point. It's like a flick book or a video camera. A sequence of stills making up a whole which seems to flow like a river. So basically, you go along to a river, right, sprinkle these dots in, this is calculus, okay? Right, that one's moving, that one's moving, that one's moving, okay? You calculate the rate of change and that gives you speed over time, things like this. And all these other relative measurements that we use as humans to measure things, basically. And obviously it does work to an extent, because we've measured loads of things, haven't we? But the Navier-Stokes equation specifically wanted a three-dimensional solution for all real-life flows, as in blood in the human body, air over the wing of an aircraft, for example, or water, just things like fluid dynamics and everything, really. But nobody's been able to work out whether there is a three-dimensional solution or not. The three-dimensional solution basically means a formula that would automatically solve and explain every single flow. So it's important to note that nature solves, inverted commas, the Navier-Stokes equations every time a real fluid flows, which implies if we could watch nature, basically watch a river flowing and measure it, then surely that would give us the results to our equations every time, wouldn't it? Because that's real life, that's what we're trying to study, real life, okay? And Navier-Stokes equations, they're just looking for a formula, basically. The equations themselves looking for a formula that will, as I've said before, the basic principle is like projecting a mathematical blanket with these specks of dust and stuff, measuring the differential between them over time. So it's as if you're spreading out a mathematical blanket that always works on top of a fluid, then you look at it, it just gives you the answer. It tells you what fluid's going to do, how a fluid might move, how a fluid how a fluid might affect things. And Navier-Stokes equations also try and account for viscosity, which means fluid friction. And as you've probably observed before, the faster you seem to go, the less friction there seems to be over a surface. So the faster the fluid flows, the less friction. The slower it flows, the more friction. Okay, two opposites, really, really simple. So all they're looking for is a basic Navier-Stokes equations. There's a river over there. I've done a study with Navier-Stokes equations. Blah 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 blah. Okay, it's going to do this. You drop your dust in. Bing bing bing. Okay, ding ding. And that's the answer. That's what we're looking for. A singular answer. This fluid is going to do this all the time, guaranteed, unchangingly. That's what we're looking for. The answer to this is there's three possibilities. 3 dimensions means 3 possibilities, okay? So you can observe a fluid and say it's going to do this, it's going to do, let's say that the viscosity is going to be a certain relative amount, a certain definition, a certain amount or something, like I say, mathematically speaking. But there's also the opposite to that, plus neutral, simultaneously, in theoretical possibility, okay? Pure thought, pure ideas, there is the opposite potential, plus neutral. So any equations or set of equations that you might make, it's simple as that. They're just looking for an answer saying are the Navier-Stokes equations accurate or not. And the answer is they're accurate, not accurate, plus neutral. Also, 3 dimensions means 3 answers. 3 doesn't mean 4 or 2 or 1, does it? It means 3. And that's why they've not been solved yet, in my opinion, because, as I say, 3 dimensions requires 3 different answers. And even if they were solved, I'd still say, well, what about the opposite to that, plus neutral? Let's say we had an equation or some kind of formula that solved the Navier-Stokes equations every single time. We could solve it 10 million times, but can we guarantee, unchangingly, forever and ever, that on the 10 millionth and first time, it's going to be the same? It may well be, but can we guarantee that unchangingly, forever and ever and ever? The answer is we can guarantee it unchangingly, we can't guarantee it unchangingly, plus neutral. As usual, it comes back to an opposite answer. They want one of 2 opposites. Are the Navier-Stokes equations correct? Are the Navier-Stokes equations incorrect? My answer is they're incorrect, correct, plus neutral in pure theory.